So I'm here at the old SLD detector hall today. You can see the detector here behind me. Back in the 1990s, this detector was running at the Z boson resonance, which is about 91 JeV, colliding electrons and positrons, just like Babar does today. Of course, it was about 10 times more powerful, roughly, using the entirety of the LINAC, whereas today we just use a small fraction of it. And, well, I came here today to talk about the electroweak force. And the Z boson is the one of the force-carrying particles of the electroweak force. The other two, the three, I guess, being the charged and non-charged W bosons and the photon, which, of course, everybody knows from light. We all see that, every day from the sun. So if you've ever studied the electroweak force, you know that it's kind of a hack. I mean, I know that Weinberg and Salam and Glashow, well, they all won the Nobel Prize for organizing it, but it really is a hack. It predicts 4 particles in addition to the photon. The 3 I just named, and then the Higgs boson. Now, they were all supposed to be about 100 JeV. And back in the early 1980s, 2 W bosons and then the Z boson were all discovered. But the Higgs wasn't. And so for the past 20-25 years or so, the big question has been, how heavy is the Higgs? Where is the Higgs? Because the Higgs is the particle that's supposed to attribute mass to the particles in the standard model by the way it interacts with them. The problem with the Higgs mechanism is that, well, it's a hack. I know you get really, really nice values for the masses of the 3 massive bosons, W's and the Z, and you get that the photon is massless, and you have nice symmetry baking, and it's just a hack, though. It's not nearly as satisfying as Maxwell's unification of electromagnetism. See, before Maxwell, back in the 19th and 18th centuries, there were 2 forces that we knew about. Well, 3 forces that we knew about. There was gravity, there was electricity, and there was magnetism. And what Maxwell did was he realized that if you made just a couple changes to the laws of electricity and magnetism, then you could group them all together, and they predicted waves, which turned out to be light. So we learned that light is an electromagnetic wave, and of course then people theorized other frequencies were possible, so you get radio, microwaves, gamma waves, all the other electromagnetic radiation that you're all familiar with. And this was, of course, very satisfying and very well done, very natural. And in fact, now a lot of places they actually teach magnetism as a relativistic correction to electricity, because it comes out most naturally that way. But the electroweak unification is not at all like that. There's no obvious corrections that they make. There's a series of arbitrary choices where they break the symmetry as opposed to creating a higher symmetry. And well, I think it's wrong. So I came here to the old SLD detector hall where they work with the Z boson to say that I think the LHC is going to fail. I don't think they're going to find the Higgs there. I think that it's probably going to be, well, the Michelson-Morley experiment of the standard model, where we're just not going to find it. I don't think we're going to find supersymmetry either, but that's a whole other issue.